Yes, please. Yes, yes. I'm
Sir,
here.
right now more than 125 have joined. So
Mm-hmm.
slowly, I think we can start the things so that
Mm-hmm.
by the time of your lectures, they will all join.
Yeah, yeah. It's okay. It's okay. Now we can start, I think, because
Yes,
initial slides, by the
yes,
initial slide we finish, many more will join. Yes. Yes,
sir,
please.
sir, sir. Sir, uh, sir, your video, sir.
Yeah, yeah. Making it on, making it.
So I welcome you to the Faculty Development Program on Advanced Optimization Technique 2025. Today, here with us, Professor Rajesh Kumar sir, who is at Department of Health Science, University of Johannesburg, South Africa. Sir is presently on leave from our Department of Electrical Engineering, MNIT Jaipur. Sir has received his BTech degree from NIT Kurukshetra and MTech degree in Power System and PhD degree in Intelligent Systems from MNIT Jaipur. He was postdoctoral research fellow at Department of Electrical and Computer Engineering at NUS Singapore. His interest focus on intelligent systems, machine intelligence, power management, smart grid and robotics. He has published more than 550 research articles, has supervised more than 30 PhD scholars and 35 MTech theses. He has 14 patents to his name. He received 3 academic awards, 12 Best Paper Awards, 6 Best Thesis Awards, and many more professional awards to his credential. He received the Career Award for Young Teachers in 2002 from Government of India. He is on the 12 journals editorial boards he is serving. He is an associate editor of IEEE Access, IEEE Industrial Electronics Technology News, associate editor of Swarm and Evolutionary Competition Elsevier, associate editor of IET Renewable and Power Generation, associate editor of IET Power Electronics. He is a senior member of IEEE, fellow of IET UK, IETE India, and life member of CSI and life member of IST. Sir has very vast experience and Sir is considered as a pioneer in this particular field of meta-heuristics. So I request Sir to uh, start his lecture. Sir.
Yeah, th thanks, Dr. Nanda. Yeah, I'm just a learner of this whole. It's a very huge, very big domain. A lot of people are doing a lot of things every day. Okay, thank you very much, and welcome you all the participants here. So good afternoon from Johannesburg, and yeah, good evening in India.
And sir,
Uh,
just before you go ahead, just 1 more minute to
yeah,
the participants, I want to tell that Sir has initially started this particular advanced optimization technique workshop in the year 2015, first time. And today on 2025, when we are doing this particular program, it is the 10th version of this particular faculty development program, sir.
yeah, that's really great. Yeah, yeah, Dr. Nanda, you have uh, taken the baton in a very nice way and carrying it forward. Still, if you search it on my website, 2015, I think the slides are already there, and now we are
Sorry,
in
sir.
25, and I can see this one is one of the most popular faculty development program across India.
Yes, sir. This year, sir, 470 participants have enrolled in
Yes.
this,
Yeah.
and every day more than 250 are joining in this particular platform, and some are on YouTube. They are joining.
Yeah, so that's really great, and I think last few years Dr. Ella is also very active in conducting this course, and I'm happy to see that the way the things are growing. So thank you both of you taking this course further and making it a more popular. Thank you very much, and let me know if anything at any stage, if you need any kind of a support from my side. I'm always there with you people. So I'm just sharing my screen, and please confirm it's
Yes, sir. Your screen is visible, sir.
okay. Okay, fine. Thank you. Let me check few things. Okay. Okay. And I think the contents are visible now.
Yes, sir. It is visible, sir.
Okay. Just 1 second, yeah. I have to, so that we can have better streaming. Stop the video here, because then maybe some.
Sir, if your video is on also, there is no problem, sir.
Yeah, it's okay, but I think then the streaming will suffer. If it is okay, then we can make it on.
Sir, please make it on. Yeah.
Okay, so yeah, thank you very much, and yeah, welcome you all on this session where we are going to discuss on DE and the variants, how people have developed variants of DE. One of the most explored metaheuristic algorithm. People have done a lot in this domain. They worked on another level of it, that is working towards the stability of the algorithms, and likewise. So in this session, we'll talk about yeah, just few slides on like optimization and what are the procedures to be followed, because many times I know earlier speakers, they have talked on this one, but it's always better to have a different view on that one. And then we talk about the procedure, that what is the correct procedure to go for this kind of such kind of a process. And then we talk about optimization algorithms, so particularly D, and then we talk about the D variants and all that. And this is the very simple from where everybody start, that okay, we talk about maxima and minima, and the simplest one is find out the gradient, and then from the gradient make make it 0, give you some stationary point, and from there uh, we can tell that it's maxima or minima, and then we go for higher order differentials to confirm it whether it's a maxima or minima. This is the simplest approach, and we know that there are this is only applicable when your function is easy, function is a smooth, function is a continuous, or the in the simple form we can say if the differential situations, if it's a differentiable. But there are many issues, and there are many things there where some kind of discontinuities or is being observed, or the problem are of different nature, like some kind of a combination, or it may be, things may be combinatorial. And then we talk about a big variety of the problems, from from linear to non-linear, then n-type, then np-type, np-hard, and likewise. And all these things comes in because every day, right from the morning till we sleep, we do a lot of things, and there we knowingly or unknowingly we try to optimize those things, like to manage those things. So those things are of different nature, and that's why you find that different types of algorithms keep on coming there. So we always look for maximize or minimize something with the given constraints, because many times we know that there are solutions, but then the constraints are violated, or may not be feasible one day. So when we talk about, we want to say we want to maximize or minimize, we always say that that is our objective function. That is because that is an objective that which we want to maximize or minimize, and if it is converted into connected with a function can be in any form. It can be in a form of some kind of a equation. It can be form of some kind of a relation between the some kind of data points, uh, or it can be some combination of both. But we call it the objective function, and summarized like it's a function which we want to maximize or minimize. And then we can see a lot of such examples across our life. Maybe some kind of manufacturing where we talk about minima, maxima. The second one is data driven kind of this thing. And now you'll find this one is very popular among machine learning, where we have observed data and we have predictions, and we try to make our models more close to the real one. So that's a basically it's a fitting experimental data, but when you are using some model to predict, and then you try to parameterize on those things there. And then we can have engineering problems where we want to maximize or minimize the cost or the efficiency or the quality factor or area, and likewise. So all these are comes under the category of objective functions, and we achieve these objective functions by varying certain variables. Those are known as design variables. And then design variables, I think already you are now aware of. They can be categorized into various forms. So you can have a binary, you can have integer, you can have a non-integer, or you can have a dependent variables, independent variables, and lot of such things are there. So we can summarize like this, that there are certain variables, and if we vary those variables, because the name itself is there, then the objective function also changes, and we keep on changing these variables in such a way that we will achieve our objective function. And obviously these variables are constrained, because typically in engineering, like you say, okay, I vary r and I'm looking for I square r losses, so make r negative, because I'm looking for minimizing my losses, which is not possible. So when we talk about varying these variables, we put certain conditions on those and certain kind of boundaries, so that we can say that yes, this is a kind of a solution which can be practically also achievable, and likewise. And there are problems which are no objective function problems. We put under the category of feasibility problems there. Okay, so this is the important part here, where many time we do a mistake. We need to check it out each and every block here when we are formulating any kind of optimization problem. The simplest part is we start with there is a need of optimization problem, because you can see the same problem with the different perspectives. There are many different and many different views, and then from some angle you can see there is a need, or there is a need from other angle it may not be, but you need to figure it out, that is it required or not required. Once you are sure of it is required, then okay, what are the variables? That is the second step, is basically that you choose your design variables, that okay, these are my variables, these are the things which I'm going to play with, and then put constraints over it, and then formulate the objective function, because now I have variables, I have a target kind of thing, that okay, such kind of things I want to do. Then how I can combine my variables to achieve that target. So formulate a objective function there, and you can see that these arrows are bidirectional arrows, so it's not like one unidirectional. It's a kind of a looping there. We need to modify and again on all those things there. And if there are certain bounds are there, put that. Once everything is ready for you, then you choose your algorithm. Just first, before choosing your algorithm, try to understand what is the type of my problem, what is the nature of my problem, what is the nature of my variables, what is the landscape, because these are the common questions people will ask you after once you complete your problem, your solution, and then when you try to put it in thesis, or you try to put it in a research article, or you try to make it as a product to sell it, then people will ask you. Uh, Typically, they will not ask on the algorithm why you have used this algorithm, but yes, in academia, people will ask you. So if you have a better understanding of your variables and the formulation of your problem and the landscaping, then you can easily answer it, and then you can find out a solution for it. So this one is a typical example, everybody knows, so I just skip this slide. Okay, and then there are classifications. So I told you earlier also, one classification based on the variables. I have single variable, I have multiple variable. Variables can be constant, variable can be non-constant. Objective can be one objective, single. It can be many objectives. It can have multiple objectives. And then uh, multi-objectives may be contradictory and non-contradictory. Your problem may be linear and non-linear, and then in non-linear, again, bifurcations are there. So these are certain classification of the optimization problem. This slide is quite old one, but still it gives just one idea that what is happening there. So you can see that variables categories are there defined. Let me take a point here. So you can see that variable categories are defined, that okay, that real variables are there, then discrete is there, then binary, then combination of real and binary, and likewise. Then the second part is objective. So we have idea about whether my objective is linear or non-linear, or it's a quadratic, what kind of it is there. Then we have constraints. Constraint may be linear, may be non-linear, may be there, may be bounded, and likewise. Some comments are there, but accordingly, then you can see the algorithms are there. So like, okay, if I know my variables are real, objective is linear, constraint is linear, okay, then there's no point of going somewhere else. I can straightforward jump into the linear programming and I can solve it, because it's already proven that for such kind of problem, this method is better. So likewise, you can see a lot of methods are there. So that's basically just to convey to everyone here that don't jump on the algorithm straightforward. Try to understand what are the variables and the objectives and the constraint, and based upon that, then think of that, okay, which method is good for my problem, and likewise. Otherwise, you can see the tree is quite big. You can have discrete, continuous, unconstrained, constraint, then integers, stochastic, and all the methods. Then they come to the picture in there. Well, it's okay. We are talking more towards a non-linear, because we know that most of the typical cases, real world problems are non-linear by nature. So then we talk about, when we talk about the non-linear, we talk about this figure. This is a very common figure. You can just Google it. You'll find this is the first figure you appear everywhere in most of the book. You'll find it. Though the function is, you can see the function looks a continuous function. But we know that there are various minimas here. This one is multi-minima kind of a problem. And then we know that, okay, if we go by the continuous function is there, if we go by conventional approach or gradient based approach, because that's a proven approach for a continuous function. We know that we trap at a local one, because if that depends upon from where you are starting. So if you are starting from here, you keep on finding the gradient along the line, and then finally you trap it here, because here you get a saddle point and you say this is minima. Whereas if you start from somewhere else on the second direction, you will reach somewhere else. So then we talk about two things, local and global. So if my boundaries are simple, this one, I want to find a solution in small zone and minimize there, we can categorize as local minima. And but if you are looking for a global space, a big space, you can another minima. And then you'll find a lot of benchmark problems. Maybe some of the speaker will talk about the benchmark problems in this course. You'll find that those figures are very complex. There are many minimas, sharp minimas, flat minimas, and all those issues are there. And that is one of the main reason why people jump from one kind of approach to another kind of approach. And if you talk about the two kind of approach, you can divide the all the optimization approaches into two categories: deterministic and stochastic. Deterministic means we know we know everything in the sense that from where we are starting. So I'm talking about all iterative process. So we know from where we are starting, and we know then the step size, and then we know that what will be the next point where I'm evaluating my values again. So everything is known. Stochastic means, okay, randomly we start somewhere, and then randomly we move to the next stage kind of thing, and we don't know. Okay, so these are the two approaches, and if you categorize them, these are the approaches which are available there. Okay, so deterministic, we know that all these are deterministic, like hill climbing, branch and bound, depth first, breadth first, best first, lambda, Newton, gradient, linear programming, interior point, and many are there. Whereas stochastic, if you talk about genetic, simulated, evolutionary, PSO, and all these things, so you can visualize that stochastic is more of inspired from the nature. They are more probabilistic in nature. There is a randomness which help us in finding a better solution. Deterministic are more kind of gradient kind of structures there, or the moment is there, which is well defined structuring. So in stochastic, when you talk about, there is one algorithm, and which is known as a DE algorithm. I don't know whether this will, you can put it here. Yeah. So DE is basically differential evolution algorithm. It is a population based. So all these methods are uh, what we call it's materialistic. They are population based. So they are basically the species, the agents which are inspired from nature, and they randomly start, and then they communicate and help us in the developing some strategy to move from one point to another and to get a solution. So it's basically based on the population, introduced in 1996 by Stone and Price, and it was developed to optimize the real parameter, real valued functions. Okay. Okay, so it's a stochastic, population-based, solving a nonlinear optimization problem. Population is composed of individuals, NP. So all are like genetic, PSO, and all these things. We have population, and it's a standard we give this a name, that NP to the population there. Uh, and then every individual in the population represents a possible solution. So now here is the difference. In linear programming, linear problems and all these things, your solution lies on the boundary. In nonlinear, solution can be anywhere inside that particular landscape. And now when we talk about why we are saying this population represents a possible solution, because we generate a population satisfying the constraints. So anything which is within the constraint, which is in the feasible solution, that it can be a solution. But what is the of best solution, that we need to figure it out. So all the population points, they are possible solutions. And there are three steps in DE. Okay. First is the mutation, like we have mutation in genetic algorithm. Second is crossover, the same like we have in genetic algorithm. And third one is the selection process. So if you talk about the terminologies, these terminologies are same as like we have in genetic algorithm, and but there's a small change here, small change in the working procedure of DE, because this works more on the differential operator. Let's see how it works there. So the flow diagram of the algorithm is the same, like we initialize the vectors. We find now here the difference vectors. We do the crossover, and then we go for the selection. So how we initialize, and I think everybody talk about the same thing here. So we need to generate few numbers, random samples, so that you can take it from this equation. And if I put a boundary over here, I ensure it that this whatever the population I'm taking, that I'm taking it, and those points are feasible one. It's not it's not non-feasible. So all the points I'm taking, they are satisfying my constraint and they are feasible one. And I'm selecting them randomly. And then we have this operator. Let's understand this is the standard figure you'll find in almost all the DE books and the articles also. So there you need to think of, like, there are three things which are there. There is a parent vector, okay, which we call it a target vector, which we targeted, okay. And then there is a donor vector. Basically, this will help us in we generate it through a differential mutation. And then there is a trial vector, and then from that we go for the next solution. So how it works there. Okay, so you can see initially we select three vectors here. I'll take the animation also. So initially on this one is taking a initial vector. Okay, and then what we can take is we can take two more also there. Two different two vectors means they are connected with the reference point to these solutions. So one solution and two solution point and three solution I have just taken. So from these two vectors, you can see here, from this vector and this vector, I find out the difference here. Okay, so this difference, then I scaled it up and then add to this one. Yeah, then I'll get a new vector. And then, so I have completed this one, and then I completed this one, and then from here I'll decide it. Let's check it in an animated form. So this one is where we are looking for a solution. Okay, so we randomly pick three solutions. Okay, x1, xr1, r3, and r2. Okay, r1 is your target one, and then rest two vectors. This will help us to move your r1 toward the solution somewhere this side. Okay, so what it will do, so what we do, we take the difference of other two. So this one is the difference of other two, and then this difference, what we can do is we take scale it up and then add it to the this this initial vector, and then when you add it, it will get a new point here. Okay, and then we check it, and then we do some kind of crossover also and check it whether this new is better than the earlier one. If it is better, accept it. Not better, we can reject it depending upon the strategy we are following. But this ensure that this point which was initial here, and maybe the solutions over here this side, so other two vectors help us to bring into the direction of it. It's not like always is that way, but most of the time it will work like that only. We can check it from the calculations also. Okay, so now we have three things here. You just take it. This one is the initial vector, this one is the scaling, and this one is the difference of other two. Now these three things will help to develop this algorithm, and you'll find a lot of variants are there in the form of how you are combining it. These are known as strategies, mutation strategy. So let's understand what is the mutation strategy. This one is one common mutation strategy. It is written like this: DE best 1 EXP. That means what? So this stands for, we are applying DE. Best means we do the operation on the best one. You can see here. So whatever is the best value we have obtained, we do the operation on that. One means we are doing only one subtraction here, one difference we are taking it. Okay, so these are the two different vectors, 1 and 2. We take a single difference. Am I not audible? Please confirm.
Sir, you are audible.
Okay, somebody is saying, that's why I, okay, thank you. So what we are doing is, here we have taken two vectors and then we take a difference of it. Now, since I'm taking this strategy of mutation, and here written as 1 means we are taking a single difference of it, and then we scale it up, and then we add to the best one. So that's why this comes DE best 1. then people may ask you what this indicate. This one is basically how you are sampling these two, how you are taking these two values. That we are following the common two methods. Either we choose exponentially distribution kind of setup there, or it can be a binomial distribution kind of there. Now you can check it anything there. Second strategy, DE, obviously random to best. Okay, so this one is another strategy. Difference is 1. So I'm operating on any kind of a random value. Okay, and then I'm following a kind of a two kind of operations here. One this one, another this one. Okay, what is the meaning here? So I'm doing the operation on the random one with a scaled value. So these two values, these two here, you can see two functions are there. Okay, you can take both these two as random and take this function here. You can take one as best one, or you can take another operator, another fraction multiplier to add these two. So it has to be basically it comes from your, you can see it comes from the old one, where you can take one set as a random and another set you can take the best one. Best 2 means there will be two differences. Best I'm operating, and you can see 2 means there are two differences. So one difference is there and another difference is there. So likewise, you can have different kind of a strategy. These are known as mutation strategies. These are, people have used it in various combinations. Sometimes they modify the best one, sometimes they modify the random one, sometimes they take the difference of random with other two random, sometimes they take a best random and modify random based upon the best and the random, and likewise. So these are the different strategies which can be used for the purpose. And then we do the crossover, because once the mutation is done, then we do the crossover. And then crossover is like, okay, so we have two values there. Okay, one is this one, another is this one, and then if we put a crossover probability, if the value is less than that, we swap it, we put the new value, we modify this unit. Okay, if it is less than or equal to, if it is not, we keep as it is. So it's just a kind of a crossover kind of setup there. So crossover, so you can see here there are two strings. Okay, 11 segments are there. At every segment we check the generate a random number, compare it with the crossover, and if it is less than equal to, we do the change. If it is not, we'll not do a change, and likewise. So likewise we can have a crossover here. Okay, and then we select it. So okay, keep on writing your questions. I'll take all the questions at the end. Okay, then so it look like this. We need to select it. So we have one here, the another two here. We find out the difference of those two. We multiply it by f, and then we take a random vector. We do the mutation. We do the crossover with the target one, which is there in the red one. Okay, and then this, after crossover, this trial vector is there, and then we select it. Whether old one is good, we keep the old one here. If the new one is good, then we replace the old one with the new one, and that's all in the DE algorithm. Let's understand by solving one numerical on it. So this is the algorithm. You can see here, sorry, pseudocode here. You can see here population size is there, dimension is mentioned, rates and everything. So all the variables are mentioned here, and then you can see here, you can see some kind of methodology is adopted, and then to do the mutation part there, and then you can see here you can use a crossover to double a crossover, and then at the end you can have selection. If the old one is new value is better than the old one, we can consider that one, otherwise we keep that one, and we keep everything in the loop. So this one is the pseudocode of it. So let's understand by using a numerical here. Okay, let's see how it will work. Yeah. Okay, so checking those things, we can see here. So let's have one example that I want to minimize this function. Okay, this is some function which I want to minimize or maximize. You can use it for the purpose. Okay, so then we can have a variables. We have 3 variable problem here. Okay, and we randomly take 6 values. Okay, randomly take 6 values. You can see here 1 to 6. These are some random values which are taken there. All these are random values. And then we substitute these values in the function and we'll get these function values. So this one is the function value. Okay, so you can assume what is the function. Okay, maybe x1 square plus x2 square plus x3 or something like that. But you put these values and then you evaluate it. This you will find on almost all the materialistic algorithms. So initially we assume some random value, variable value. That means that is a solution basically. So this is a solution what we are having on the screen. That is the solution in the 3-dimensional space. Okay, and once it is there, then we substitute into the function and we find out what is the value there. Okay, fine. We now go for the D working here. So this one is our target one. Okay, on which we are operating. We choose 2 random ones. So say here we have taken number 2 and number 4 as a random, and then we find out the difference. Okay, this is the difference which is obtained. That is a simple process, and then we multiply it by a factor. So don't, it is not 0.08, it is 0.8, please. Okay, so we multiply it and we'll get these values. So we multiply the difference and then we get a values there, and then we add it to another one, another vector. So some people call it noise also, but this is the another vector which is 6. So we add these values here, you can see here. So now this one is the new vector. Okay, and then this new vector we go for a crossover. So what we can do, we can put a CR safe probability of 0.5. This one is the target vector which comes from here, straightforward, and this we obtain it from here. So for each value we check it, we check crossover. If it is more than or less than 0.5, we change it, otherwise we keep it what is there. So in this case we keep this value as it is because the value is not satisfying our conditions. For x2 it is satisfying, so we replace this value here, and in x3 again it's not set, maybe it's satisfying likewise, so we replace this value here. So now this one is the new vector, this one is our old vector, this blue one. And now what we'll do, old vector value I have 1.61, new vector I will evaluate it. If new vector is better and I'm looking for minima, and if this value is less, then I replace it here. If it is not, then I keep my one as it is, and for the next value, okay, for the next value I'll go for the second one and repeat the same thing, and then I go for the third, and then the fourth, and the fifth, and I keep all these things in the loop. Finally you will find they converge and give us a better solution. This is how the D algorithm will work. Okay, so okay, there was a question, you can check it. I think you've missed this slide. This is the condition here. If the random number is less than CR, I'll do the change. I'll do the change. If it is not, I'll not do the change. Likewise, CR value you can choose it because that is same as like what we do in PSO or what we do in genetic algorithm. Everywhere we have some kind of a values there. We call it the crossover rate and likewise. But this is now important aspect. Somebody pushed the question, and that is how people start developing the variants here. So what are the parameters which we can play with? Okay, and the parameters which we can play, 3 are the very simple one. These are the 3 simple one. Okay, first, how much should be the number of population? So you increase or decrease the population, or the initial feed, how you are feeding it. Okay, you can take you can take some samples there, and then think clear now for everyone. Okay, so we will take some samples. We can take samples from distribution, or also at the same time we decided how much is the number of samples to start with. The second thing is the factor which can play with is CR, because that help us in the crossover, that how the crossover will occur. Okay, and the third factor is the F, that is the scaling factor. So these are the three things which are there in our hand to develop a variant. And another one is the mutation strategy, because you have mutation strategy there also you can play with. You can find out single difference or double difference or binomial distribution or exponential kind of setup. So two general categories are there. Either you can make your whole algorithm self-adaptive, that means your algorithm control the parametric it will do with certain kind of a rule regulation. And in another case you can take it like, okay, in your looping you put certain kind of arrangement that it automatically modify that one. Both are self-adaptive. They can do these changes, but in one case I'll make a rule. I make a rule something like, we'll see in the coming slides also, like I'll take the value from the distribution. In the second way I'll say that, okay, with every iteration change it like this. So depending upon how you are doing it, all these stuff. So this one is we talk about, let's say, deterministic parametric control. Okay, so one of the approach is like this. This is one of the variant. So you use a deterministic rule. Okay, regardless of the feedback, whatever the feedback, I don't care, but my rule is fixed. And what they did in that one is basically they put that F is in this range. Okay, and CR is in this range, and then we have to take the combination. This is known as composite DE algorithm, CODE. You can see here what is CODE algorithm. So I have some combinations. So these are the three strategies I'm going to take. That is the first thing. Okay. Okay, so this one is there, and then we have a combination. Like if I take F1 combination, I take F1 CR.1, F1 CR.9, F.8 CR.2. Just three pair of choices, just to make the thing simple. And then what we do, this one is a combination, like first trial vector, first control parameter, first trial vector, second control parameter, first trial vector, third control parameter, second trial vector, and likewise. And then you can have multiple things in your hand, and from there you will get the solution. This one is basically one kind of the variations, because it is always a challenge in the algorithms that, okay, what is the best setting for your CR and F and NP. So this is the thing that, okay, instead of that, what we do is we take a set of CR and F values and the strategies, and then let's have a combination of that one. That is the first variant. Okay, and then that's the same there in the algorithm also. Then that another one is, which is very popular, that is basically, instead of, because it looks bulky, like how many combinations I'll take, what combinations I'll take, and we are fixing the parameters manually kind. So another approach which is very popular, and that is adaptive parameter control. We are let the algorithm to update the parameters of your node, and that is basically based upon the feedback. So you take a feedback of the values and then modify. And these are the some of the variants. There are a lot of variants. Some of the variants are, few of them are very popular also, like your cell differential evolution with self-adaptive population, fuzzy adaptive differential evolution, self-adaptive differential evolution, self-adaptive NSDE, self-adaptive parameter setting in D, that is JDE, ADE, MDE, and likewise one of the popular is Jade, and then Shade, and many more such are there. Let's understand what changes they have made, so that Okay, we have idea that how we can develop a new variant for our problem also. So like in this one, DSAP, basically it dynamically adjust the parameters. Okay, initially it was designed for Dijon exam problem, and what it is changing is basically it is basically working on the calculation of the probability. Okay, so f is basically static, but your crossover is this is the notation they have taken. So crossover is basically depends on the probability theory, and then they use the normal distribution. So they sample the things and the distribution, they calculate the probability, and then they use it for their purpose there. Then comes the fuzzy adaptive. So what is the change in fuzzy adaptive? Let's take this figure. Okay, population, we do use a D as it is. We evaluate, okay, and if termination criteria is not fulfilled, we come out, but not fulfilled, then what will happen? And then we use fuzzy logic here, fuzzy settings there, to find the parameters, crossover, mutation, and reproduction, and something same thing. So selection, crossover, mutation. So we find out these parameters, and then once we have these values, then we put these values in our D algorithm and let the D algorithm to calculate it. So this is basically, you can say, we are putting a controller there. Okay, so how much is the error? If my error is more, I put a fuzzy system, it evaluate. Okay, if your error is high, do this change, select your crossover has to be like this, mutation has to be like this, and then put it there back into the DE algorithm, and then DE algorithm will work. If this arrangement is done, this is known as FADE, fuzzy adaptive DE algorithm. Then comes the another algorithm which is known as self-adaptive DE. Okay, so it's in self-adaptive DE is like what they have done here is, this is said, they have taken two strategies. Okay, this is one strategy, this is another strategy, and then they attach a probability. So they said they attach probability p with this, and then 1 minus p with this. Okay, and then what they have done, they generate a random number, and then from here there they can find it out, that it is near to which one, and accordingly they go for the mutation strategy. Okay, so that's the difference here, how they are shifting between the two of the majority. Then some kind of corrections they have done it, because what they have done is later on, they put the solutions there. Okay, so now they have two sets. One set, because when you put into the any kind of a strategy here, any kind of this strategy, you'll get a new vector. So you have two vectors, or two group of vectors. One group of vector is basically successful. Successful means they can go for the next round, they are not violating my conditions and all that. And the second set is, which is non-successful. Then they use both these two sets of successful and non-successful to calculate the probabilities. So you can see here, S means successful, F means failed. From there they calculate the probability, and then they use this probability again to go for the to decide which type of mutation strategy is good for you or not, something like that. Okay, so this one is uh, uh, they did it for mutation. Then comes the another what modified version is, that is self-adaptive NSDE. Okay, so this is again the same kind of thing, but you can same kind of setup here, but the difference here is basically in the distribution. So they have used Cauchy distribution instead of a normal distribution. That's the difference. And then they come out with this kind of a approach, which is known as SANSDE. Then comes a self adaptive parameter setting with another variant there, and that variant is basically depend upon the two random variables. So this one is simple algorithm where you can take, I set two coefficients here, and then I attach generated two random numbers. Okay, so if my random number is less than this, then I modify f again with random number. You can just see the difference here. Otherwise, I'll go by the old one. Similarly, in the C, if my random number is this one less than this coefficient value, I'll generate a random number for CR. Otherwise, I'll go by the old CR. So this is how again they are changing it. Where sometimes they are totally based upon totally on the random number. Sometimes they are generating the number from a distribution, maybe a binomial or Cauchy or Gaussian kind of setups there. So this is all about how they are combining these setups there. Now this one is adaptive D, AD, which is more like, you can see, if you see the PSO and all that, okay, there how you are changing your omega or C1 or C2. Some people uh, modify or update it by a linear decrement, some go logarithmic, some go stepwise, likewise. So such kind of such kind of observations are there, which help them that, like, okay, we can modify how you can modify your CR there. That is comes in basically ADE. And then comes a MDE. So they use an array, they use a Laplace distribution. So that's the change here. And then array is updated every time, and from there the solutions are values are to modify your crossover rate and your f. Okay, so this one is again kind of a setup there, where they have modified by using putting a ceiling and going for a certain kind of calculations, which is basically NP is basically what you already fixed it, and they have calculated GE and the number of generations. So they make it a function of generations just to push it. The distribution is Cauchy, but they want to push it hard uh, that the convergence should be faster one. Some other one like this one is another variant there. I think this is not moving anyway. Otherwise, you can check the things here. They use 10 function there to calculate your f, and then this kind of a relations for your calculating your C and all that. This one is very popular, shade algorithm, where you can see here, this one is, sorry, Jade algorithm, where you can see there are different kind of strategies here. So they follow a basically greedy strategy along with the classical one, and then they take a union with basically between the two approaches, just to make a balance between the classical one and the greedy one. There can be multiple strategies also, single one, and then you can follow multiple strategies. So what you can do is you can make a pool of strategies, and then from the pool you can select the strategy. Either you can select it randomly, or you can follow as another strategy on that one to select what should be your mutation strategy. Such kind of arrangements are there. One is this one. Okay, and this is basically hybridization, we call it, like DE with PSO. So you can see here it is working as DE, but if this condition is not satisfied, then your PSO is activated, which will help them to find a new particle. And then once it is there, then again D starts coming in. It's a hybridization of PSO and D, and you can hybridize in various forms. You can use PSO here, you can use PSO here also, you can use PSO somewhere else also. So this is totally depending upon how you are mixing the two algorithms. So in this algorithm D PSO, this one is D is working fine, 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 but the solution is not getting better. Then okay, you activate a new particle with PSO, and still if so, you have to think of like the criteria when to stop and all those things that matters here now, because every time it may be possible that when you are saying that okay, there's no improvement, and that may be the good solution. So it's not like always you keep on activating a new PSO and likewise. So though there you need to figure it out how to stop your algorithm. And these are the few algorithms where people have combined like D with ABC, D with ant colony, D with bacterial foraging, D with gravitational search, uh, and then DE with IWO, D with Firefly, and these are the certain kind of problems people have implemented. They have implemented on the real objective, engineering problems also, clustering problems, single objective, multi-objective, binary optimization, depending upon that. And all this comes because everybody speak on this one, that is new, that is basically no free lunch theorem. No single algorithm is good for all of the problem. So you can try on making the combinations. Even you are combining say D with ABC, but the important is how you are merging your ABC into D, or you are merging D into ABC. That give us different kind of solutions. Okay, I think I am in time. Yes, it's 1:31. Okay, so now I'll take your questions, and I can see a lot of questions people are pushing in between. Uh, Let me stop the presentation. Stop sharing my screen. Now I can open my chat box. Meanwhile, if you have any question, what you can do is you can unmute, you can put to me, else you keep on writing the chat box. I'll take one by one and try to answer your questions. So good afternoon, and then okay, voice audible issues, okay. So, okay, one question is want to know the difference between PSO, DE example. I think I have shown you one example that how DE works. In PSO, it is basically a difference. Again, there in PSO, it's a difference of the two values. So if I take it that way, that I'm going for a DE slash random slash 2, that means I'm working on the two differences, then I can say that, oh, it is somewhere near like a PSO, because there also we calculate two differences, difference with the personal best and difference with the global best. But the approach is different. In PSO, we don't go for crossovers and all those things there. So that is basically a difference. And I think I have explained D with an example. So now you can easily understand what's the difference between the two approaches. What is CR condition? It's a crossover probability. You can take it. We know that how good it is. So that is one of the issue with this algorithm also, that how to find out CR. And that's why people go for adaptive calculation of CR, that okay, instead of, because it's difficult for me to choose the CR value, crossover rate, uh, uh, because maybe I don't have complete idea or knowledge of my problem. So instead of doing that, why not to go for adaptive one, so that it can automatically or uh, can find out the most optimal value for that kind of a condition there. Okay, canvas, is there any relation between two random variables for that particular case? uh, it's not there, it's taken randomly, but we can develop a new kind of a variant there. And this is a very good question from VSD, that can we develop a variant where, okay, we have some old distribution, and then we have a distribution which is new, and if we can find out a relation between them, or what we can do is from the some old distribution, using some kind of transformation, we find out new distribution, and then we take two random numbers from there, how they are affecting it. It's interesting to see that one. So there is not a relation, but you can think of creating some kind of a mapping between the two distributions, and from there you can take random numbers from there. Is this algorithm built in MATLAB? I think in new version it is there, but otherwise people have already put this D algorithm on the program on the websites. I think I have also put it long back. If it is still there, you can download it from my website. So most of many PPTs and the codes are available from my website. You can download it from there. Okay, so the question is, and it is in context of GA and impact on GA performance. Okay, so that's again that's I'll say a different discussion will start from here, because if we talk about uh, this part here, but I think if you uh, studied on that part, there basically you how you want to make it's a dominance. So here you can do it. Like again, I'm trying to add it to one of the idea which somebody has done already. Can I have one distribution up to some iterations, and then from there I'll put some kind of a dominance strategy for the next value calculations. Uh, Maybe I can put it that okay, now I'm putting a listism into it and then trying to getting those values there. So question is there any way to initialize control parameters optimally? So we don't know the problem, because and what we are doing is with iterations, with the feedback, we are modifying our control parameters, and initial values. If you have idea about the somewhere an idea about the problem, then you can take the uh, values there, and that is basically that's why people are hybridizing it. Yeah, for simple problem you can take it some standard some already some articles published in that one, but we are looking for improvements and all these things for more complex problem which there we don't have much of an idea. Then well, that's an interesting zone of research that okay, you do landscaping and then follow some kind of a pattern patching and all that, and from there you can think of okay, these are the good initial feeds for my algorithm. But the simplest one is let my algorithm to take a feedback and modify up automatically and likewise. Okay, so there are some stopping. What are some stopping conditions? Okay, so in GA the stopping criterias, like okay, people say okay, I fix the number of iterations that okay, whatever be the result, but stop my algorithm after 5,000 iteration, it stop. That is one of the stopping criteria. Second is okay, if my values are in this particular band, uh, uh, band means last 10 values are they are changing, but they are changing in this band, then I can say that okay, stop. If they are not change, that means okay, I'm happy with the happy with the solutions I'm adopting. So that can be another stopping criteria. uh, some other criteria is you are solving some engineering problem and then you are obtaining some solution, and then you can fix it that okay, if my solution is in this range, that is my tolerance band is so much, and if I achieve the solution in that one, stop my algorithm. So there can be many possibilities or many ways to stop the algorithm. Okay, so these are the questions here. I hope I'm able to answer it. If you have more questions, put it. I'll be happy to share, answer you. I can share my link of my, I think if it is still working. So you can download many things from there. Many PPTs and codes and those things are available. I'll put very soon some more algorithm and codes on the website and put more PPT so you can download it from there. I'm just in the process of updating my website, so you can download it from there. If you are interested in developing a new code or new algorithm, so tomorrow I'll explain more on developing the how we can develop a new algorithm or how we can design a materialistic algorithm. So if you have any query, if you are interested in that one, you can okay, you can mail me. Uh, I'll I'll answer your things very quick. That is that is certain within a half an hour, so you'll get your answer. And if you're interested, let me know to work on some of the problems there. Yeah, okay. Thank you.
Thank you, sir, for this lecture. and we will be waiting for your next lecture tomorrow, scheduled the same time.
Yeah, I'll be there. Yeah. Okay. And
You have already
yeah,
shared your website's link to the chat box.
yes.
Any query will
Yeah.
be
So
there, so they will
yeah,
be.
if they have any query, just they can mail me or collect the queries, and probably we can discuss tomorrow also if they have any question over the things there.
Thank you so much, sir.
Yeah, thank you, ma'am. Thank you, Dr. Ila, and thank you all the participants here for listening me. See you tomorrow. Thank you.
Thank you, sir. So the